on an example, because like this, I'm sure that some of your questions will go away with something simple where we don't have to think much of derivatives. Well, okay, double variable function 2x squared y x squared y plus, I don't know, something like natural log of xy. So the total differential, like, see the way I write it, it's not anymore dg over something, because for the total derivative you can still only do it with respect to one variable. Even though it's a total derivative, it's still with respect to one variable. So here what I want is the absolute change of g given other things change. And in here, I don't know any correlation, any relation between x and y. Maybe there is, maybe there isn't. I'm not giving it and I don't worry about it. Okay, perfect. So now I'm supposed to find a partial with respect to x. And that will be 4xy plus y over actually it will come to 1 over x. So the partial derivative of this, where I'm treating y as constant, that means what? That means I'm supposed to first take the derivative of the outer function, so of the ln, I would end up with xy here. And then I'm supposed to multiply by y, because that's the derivative of the inner function. And they cancel out. And it's not difficult to guess, because this logarithm can be split into a sum of ln x plus ln y. And if y is a constant, ln y is a constant, and well, its derivative is 0. Okay, so the way we write it is like that. dx plus, now we take partial, so with respect to y, that will be 2x squared, because here 2x squared is just a coefficient for y, plus the same thing will happen here, so we end up with 1 over y in this case, dy. So that's what you were supposed to do. That is total differential, because this is the rate of change with respect to x, and we multiply it by how much actually x increased. This is the rate of change with respect to y, and we multiply by how much actually y increased. Again, this writing dg dx dy means the increment. Okay, so I'm giving you some time, some 5 minutes to solve the first 3 or the first 2. Let's see how much we can do in 5 minutes. Let's check it, and then we move to the gradient and the directional derivative. Okay, let's check. First one. Okay, before we check, I need your pluses. If you did, how many? If you did 2 of them, all 4, okay, we have all 4, 4, okay, yeah, that's what you should do, put the number, 3, 4, 4, 3, 2, okay, okay. Great, so let's check the first 2, and then the rest will go to your homework, and if you did it already, you have less homework. So we're starting with first dg. Here the derivative itself is simple, just get used to this notation of something dx, something dy. and 12x squared plus 3y squared plus 2x plus 4x y punto dx plus here now we're taking it with respect to y, and with respect to y we're gonna have 6 xy plus 2x squared plus 3y dy. Okay, so give me pluses if you agree with this. Okay, I think you agree with this. Perfect. Great. The second one. We're gonna have, since we're having 3 variables, we're gonna have 3 terms in our sum. So dg, the partial for all of them will start with the same 2 times 2x plus 2y plus 3z, because this is an outer function for whichever. And then for x, that's it, because then the derivative of the inner with respect to x is 1. Then for y, we will multiply it by 2 as the derivative of the inner, so we're ending up with 4 times this thing. And then for z, it will be also dy. It will be then multiplied by 2, multiplied by 3, so we're getting 6. Tan tan dz. Okay? Is that okay? Tiny square is missing. Where is the tiny square missing? Here. Yep. Yes. Okay, cool. So you got the idea. You just take a partial derivative and then you write d whatever x dy dz. Okay, cool. Yeah. The third one, you will have something like 1 over 2 square roots, and then in the numerator of each one you will also add 2. Yes, exactly. It's supposed to be plus here. And so for the third one, some things will nicely cancel out, like 2 in the numerator and the denominator. And then, well, you will always have the same dx, dy, and then the last one, well, product rule or just expand it, and it will turn into something like the first one. Okay, so now let's move to something that is very interesting and it's gonna be super confusing. So, we saw partial derivatives represent the rate of change of x as we vary, of f as we vary x, holding y fixed, and the other way around. So depends. If we take a partial of f with respect to x, that's what we have. If we take a partial of f with respect to y, then we hold x fixed. Okay, perfect. We know that there is the idea of total derivative, but as I told you, we can use it, like we can have an idea of not holding the other equal and what will happen, how much will our g change, or f. Only if we have this functional form, so only if we know what's the relation between them. But what if either we don't know or there is no? So like, for example, two absolutely unrelated goods in our utility function. So, I don't know, Ferrari and baguette, right? So we cannot say that they're complement substitutes. We cannot even think of a grade of substitution, right? Well, absolutely unrelated. So this is our case. So what do we do here? Well, we have some nice idea of a directional derivative. And before we get to that nice idea, we should get acquainted with the notion of gradient. So, how to find the rate of change of f if we allow both x and y to change simultaneously, and they will change in whichever direction. So, for example, we find ourselves at a certain point, and then we say, well, what happens and how fast will f change if now we increase x twice and decrease y, or we increase both, or we increase y by we increase one, but we increase the second one a little more. So many options here, and we need something that will allow us to get actually a number, right? So what I want to know, like, by how much? What is the rate of change? And I'd like to show you on a graph, but I think it's gonna be more of confusion than anything else. So we know about normal derivative that it can tell us also whether the function is increasing or decreasing at this point, because, for example, if our derivative of just one variable function is positive, then we understand that the function here is increasing. If this derivative is negative, we understand that it's decreasing. And here we can also get a final number like -3, even if we start with this confusing notion, we change both x and y, and we change them the way we want. And then we can get how f changes, and we can get if f in this point is decreasing or increasing, and by how much. So you should now start thinking of more of three-dimensional graphs, because we have one axis for x and y, and now they are independent variables, and then we have another axis for f, for the value of function, and that will be our dependent variable. Okay, so before we get to directional derivative itself, we need to introduce gradient. So in general, we're able to get a vector representation for the derivative in multivariable case, and we call this thing gradient. So if we are not able to find a total derivative, but we still need to know what's happening with our function if we allow for both of them to change, or for three of them to change. You know, now I'm just taking two argument functions. This same logic will apply to three argument if we have 3 goods, 100 goods, whatever. Okay, so we have gradient to take care of. And let's make it clear since the very beginning, gradient is a vector. So you already know what's this and this. So G and F, here you should think of them in this way. So G is f of x and y. F stands for function. So when I say here this, I know how it's called, nabla, right? This letter. Whatever. Gradient of f, it's partial derivative of this function with respect to x and partial derivative of this function with respect to y. So using this notation. I understand that it can now get confusing why we have f and g, but just think of it like this. Here we had no problem, so let's keep it this way. I could write here the gradient of g, but well, whatever. Cool, so partial with respect to x, partial with respect to y. And it is a vector, so it means that it indicates us into some it indicates some direction. Let me actually show you the three-dimensional thing. So do you see now my word? Please put plus if you see word. Oh, I had some questions. As an example, if the utility of x and y is x squared minus 1 squared, using the gradient, I can see how u changes if x changes and y changes. Exactly, right. And if they change simultaneously, and I just have to set by how much of both of them change, and I will see how u will change. Okay, you all put pluses, so you all see my word. And let's create a three-dimensional space. Whoop. Whoop. Okay, so this will be x. Doesn't matter. Like, I just prefer having here x. I'll make it pretty later. Here y, and here f, the value of function, g, f, whatever. Just this is our independent, dependent, and I want to keep it like straight like that. And these two are our dependent variables. So when I calculate gradient, the function here goes, how does the function go? Well, let's make it go, I don't know, like that. Pretty. Okay, so it is supposed to actually not be like a line, it's supposed to be a surface, right? But let's keep it like that, knowing that this is a function, then going somehow, somewhere. And at each certain point, we're able to get our gradient. So, for example, if we start from here, we calculate a gradient, and that will be a vector, and this vector will be very fat and orange. And so this vector will be in the coordinates of x and y. So this is a direction. Now imagine that you only consider the plane xy, and there is the vector corresponding to a gradient. So again, back here, when you calculate it, first you can get it in general form, right? So both this thing and this thing will be functions of x and y. But then if you place yourself into a point, you can substitute x and y in those functional forms by values, numbers, starting like if we started here, we'll get it, and you will have just two numbers. So two numbers for a vector. And what is really great about this gradient vector is that it points in the direction of the greatest rate of increase of the function. So it was not random that I put it here like that, because function greatest direction of increase is there. So you're not gonna need it per se, like, you know, learning by heart that the gradient points in the direction of the greatest rate of increase, but just I'm giving you this nice feature of the gradient, so you are able to later understand why are we using the gradient. So we just have to set a point and we will straightly find the direction of the greatest increase of the function. Well, since we have a three-dimensional space here, we have to deal with vectors. Okay, so is that clear for now? The course is upward circular. No, yes, no, I don't know, I just put random blue line. Yeah, maybe. It really doesn't matter. It can be whatever function. And as I said, it should be actually a surface. Now indicate coordinates in 2D. Yes, this vector indicates coordinates in two-dimensional space, x and y. So the first one will be with respect to x and the second with respect to y. And the direction will be indicated within this plane yx. Okay, let's have some more questions. Some more questions? No? No? Okay. Exercises. So find gradients for the following functions. And let's have it. I want to give you some points, but I don't know where to write it anymore. Okay, find first gradients in general form. That will be super fast, so I'm giving you really like 2 minutes. The time I download this PDF and start a new one. Okay, I don't like it. Okay, I like it now. Yes, everybody can hear you. I don't know what the fuck was that. Elaborate more on the economic front of a gradient. Yes, I might. Well, actually, I didn't want to because that will be your first lecture in microeconomics. You will start with that and you will see this in a case of maximization of the utility function given budget constraints. So you will see it through the gradient. And if I see that everybody is super comfortable with the notion and with the calculations, then I will show you some underlying meaning. But well, Professor Seki will do it for you for sure. And maybe, I don't know, like last year I decided not to do it and leave it to him because like this you only know one way of explaining and you don't get confused. How to actually find a gradient and which slide are exercises on? Wait a second, I finished the downloading and then, so I'm sure that you have it. And then I'll show you the whole thing and one example before. So first of all, answering the question of which slides are exercises, it is slide 15. So it's called exercises gradient and it says find gradients for the following functions. And let's, before that, consider one example. Let's talk of it already like of a utility function. So this is u of x and y, and let's take the, I don't know, like ln x plus ln y. Okay, so the gradient u will be equal to I think, yeah, okay, whatever. So here I'm supposed to find the partial of u with respect to x, comma, partial of u with respect to y. So it all comes to calculating partials. So here what we have is 1 over x, comma, 1 over y. Okay, so that's all I want for now. Wait. That's all I want for now, right? So just give me partials, and then, so this is the vector. This is the vector's coordinate on the x-axis, and this is the vector coordinate on the y-axis. And for now it's in a functional form, but I can always give you a dot where we start from, and you will have no problem with finding actual vector numerical. Is it wrong to do a system? Which system? Where system? You can unmute to explain what you mean by system, Antonio. I know where you were doing the system, and it was in the optimization, and actually your system looked like partial with respect to x equals to 0, partial with respect to y equals to 0, and that's slightly different. So that will be on Tuesday. We will do that. And actually some nice news about next week lectures. I will try to record them on my computer. If nothing else better comes to our hands, as in like maybe the university can provide us with a kit to record, but I really highly doubt it. So in the worst case scenario, if nothing works, I'm just gonna record myself and the blackboard and the slides with my computer, and you will have at least something in hand to see. Okay, so gradients. Okay, let's check, and I will also give straight some numbers so we actually get an idea. So find the gradient for the following functions. So for the first function, g, let's call it, yeah. What we have is, wait a second, don't like it, but don't want to look for the other one. Simple. We're gonna just have 6x, comma, 12y squared. Nothing more, nothing less. Okay, so this is a general form, so for now it should be very confusing, especially if you don't remember vectors very well. Like, what is this vector and which direction does it point? Well, no idea. So let's get it at a point, and the point will be the 3, 1. What does it mean? It means that now we're starting, if we go back to our plot here, we're starting at some point here, that x we're taking 3, y we're taking 1, and there is some point on the function, right? Well, on the function, yeah, like some point, let's say that it's this point, that corresponds to these two on x and y. So up, I need you now, and now I need your space positioning. So y equals 1, x equals 3, and there is a certain value of f that corresponds to that, like it's somewhere here. We can actually calculate it because we have the functional form. So the gradient at this point will be 18, 12. I just substituted, replaced x with 3 and y with 1. And why am I doing it in this function? Just because, why am I doing it with these numbers? Just because I invented them, I came up with them. Maybe for some reason I need the directional derivative starting from this function. And we can get the value of the function as well. So now let's focus a little bit on what this, the vector leaves from the origin and reaches the graph on the xy plane. Exactly. So if we consider xy plane like flat in the bottom, there will be some vector and it will move and get to the function. You got it perfectly correct. So I'm gonna try to explain it now. We got some vector 18, 12. If I'm just doing it on the plane xy, so this is x, this is y as always. So I'm supposed to find the dot. What is it? 18, 12, right? So here I'm gonna have 18. Up 18, and here I'm gonna have 12. So yeah, I know, but well, you understand, right? So perfect. How does the vector go? Well, this is something from high school. The vector will be up like that. So these two coordinates are pretty much the coordinates of the end of this vector. Let's do it, I don't know, gray. No, doesn't help. Let's do it very yellow. So these yellow lines that I'm now trying to put, they're just showing you that 18 and 12, they are the coordinates. They are the coordinates of the end of these vectors. So now you can see that, well, this is obviously well-defined direction, right? So now imagine that this direction, this vector, is somewhere here. And then we can lift this vector to this point, and it will now, well, let's make this, this is the vector, right? So let's make it, let's make it black. And then this black vector will be somewhere here. I'm not so sure that I'm just putting it randomly, right? Because I don't know the function and anything, but that will be the same vector, so it would be just lifted and placed to the point where we started from. And this lifting is a parallel transformation, so the vector, this black vector, is absolutely parallel to this vector. Okay, so do you have any questions? Wait a second, I'm losing my conversation. Okay, do you have any questions? So what is the gradient? Gradient, first of all, is the vector. That's how we should start our definition. The gradient is the vector. that points in the direction of the greatest rate of increase of the function starting from a given point, right? So another way to define it is that it is a multivariable representation of a derivative. But what I want you to capture right now is that it is a vector, and we can calculate it for each point of our graph, and it will always point in the direction of the greatest rate of increase of the function. And speaking economically, let's add something. So the gradient always has to point on a point on the function. It always has to start from a point on the function and point somewhere, and the direction will be the direction of the greatest rate of increase of the function. We cannot actually draw this vector without knowing the initial point where we start, because without knowing the initial point you just end up with something like that, and it's cool, but well, it doesn't give you any idea, right? So but it makes sense because at every point the direction of the greatest rate of increase is different, so it really matters if we start from here, if we start from somewhere here or from somewhere here, right? So yes, perfect. So now is it related to Euclidean distance to calculate it? No idea, being honest with you. Or if you explain to me what do you mean by Euclidean distance, I can maybe tell you, and you can unmute.
So the Euclidean distance is kind of using it within the vectors of, in the case we're trying to calculate the distance of two vectors in order to find a greater one. This is
What you mean is okay. Okay, this is actually great that you know this formula because we'll use it, but it's not related. No. You shouldn't think of gradient in this case. Yeah, don't listen to that. So the greatest rate of increase is just a direction. Good question. I cannot say yes or no. It should be stated a bit in a slightly different manner. So you understand that if we start from this point, we know that function from this point is maybe at the same time decreasing somewhere and increasing somewhere. So it's like, well, if we're talking just two-dimensional, let's consider it real quick here. Dun 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 dun. And we have a function that goes like that, right? And now imagine that we are at the point here. So we see that from this point, it depends on the direction. So if we move here, the function is increasing. So it's gonna be a green one. And if we move here, the function is decreasing. So it will be the orange one, right? So where will be the greatest increase? Well, it will be this direction. In two-dimensional, it doesn't make very much sense as in like pointing, because you can see that obviously for this exact function, this is increase and this is decrease. So, but that's the idea, right? So we know that if we are at a point, then we can go somewhere where the function will increase, so get greater values, and we can go somewhere where we can get lower values, and it's determined by the direction where we go. We go on the left, well, something happens. We go to the right, something happens. So, do you mean the greatest change, no matter if it is increasing or decreasing? No, I mean the greatest rate of increase. The greatest rate of increase. And we can have, depending on the function, depending on where we start from, we can end up with the idea that, like, there is no increase. It can happen. But, well, no, I'm not gonna say anything that's gonna be confusing. So, in microeconomics, this will be very helpful for understanding how can we maximize a utility function, right? Well, we will already have a vector that will indicate us the direction of the greatest rate of increase. So, you know, that's the first step to maximization. Okay, so that's a little bit of economic context for you. Great, perfect. And now this is going to get worse, and I really want to start it today. Even if we don't finish it, and even if you stay a bit confused, it's okay. So I gave you the exercises. I'm pretty sure that you managed to find partial derivatives here and here. Now let's look at the directional derivative. So the directional derivative will be a number. So when gradient was a vector, directional derivative is a number. So here we're going to end up with something that we already saw. We can calculate a derivative at a point, right? So for the function, I downloaded it, right? Let me just check real quick what I downloaded. What is this last one? Okay, what is this one? No! Why? Okay, I really don't want to lose that part. So what we're gonna do is continue down here, and if I'll have to split it in two later, I'll do it. So let's consider one variable example. My favorite. And no, that's not going to work for what I want. So the derivative of this function will be different at different points, right? So as we already checked, first it is increasing slower, and then it starts increasing faster. So imagine that I want to get the actual value of the derivative. So I want to know how fast will my y increase given I start at a point 3, right? So I am having the derivative just y prime x is equal to 4x, and now at the point 3 it will be 12. Okay, perfect. I'm getting it. So this is just one variable case. So now for the multivariable case, we'll have to work a little bit. So this, the same way, the same final value will be given by a directional derivative, and I have one more question. Could you give the solutions of them? Will it be a homework for the 16? Yeah, you understand it. That will be a homework. So, partial derivatives of this not that bad of functions, I think you can find by now. So that's another exercise for you to find partial derivatives. And in the very end, what I want is this. So you're not given any points here for G and G. So you will just have to write me corner, partial derivative, comma, partial derivative, closing corner. So that's it. Directional derivative again. So directional derivative will help us to do this, but for multivariable case. And now we're able to choose a point where we start and study the change of the multivariable function there. Well, for the gradient, I was also choosing a point, so you're more or less familiar with that. But we also need to choose a direction of the combined change of x and y. So in case of the gradient, we didn't have to do it because the gradient is the direction of the greatest increase. But now let's say we don't want the direction of the greatest increase. We just want to know by how much f will increase if x is increasing by 2 and y is increasing by 3. So we need to choose this direction. And it will be given by a vector. So this idea again. So by how much? By 18 and 12 or by minus 17 and 2? And what is very, very, very crucial here is that we need it to be expressed as a unit vector. And now follow me here. So let's take this vector. We already are familiar with it. So unit vector is the vector that has a length, right? The length of the whole thing equals 1. So this is what Lucas is calling Euclidean distance, the actual length of this vector. And in this case, so in the case of this picture, we can see that this vector should be, well, longer than just 1, right? Well, we have 18 here, 12 here. How long is it? We don't know. Pythagorean theorem helps us to find this length. This is hypotenuse, right? So we can actually find the length of this vector. Let's do it. So, how do we get a unit vector? So, imagine we have our 18, 12. Its length, I want to use length because, well, we all understand what's length and we don't have more terms. So its length, Pythagorean theorem, is equal to square root of 18 squared plus 12 squared. If you don't understand how I got it now, please Google Pythagorean theorem and how to find a hypotenuse. Okay, perfect. So you see now this vector, right? If I decrease it like that, the direction is not changing. So it's still pointing in the same direction. I just made it a little shorter. Well, much shorter. And to actually get these now new coordinates, what do I have to do? I have to divide the existing coordinates by the length. So that's quite intuitive. what I'm doing here, because I had a vector of this length, right? So if I now divide this by this length, I'm getting 1. And that's what I want. I want a vector of the length 1. And why do I want it so bad? It's just because when we're given the direction like that, 18, 12, the same direction can be given with an infinite number of options. And for our directional derivative, we actually have to stick to something like one option, right? Because we can give this direction of change like 1,000 ways there are to give it, but which one do we choose? So the one that we'll choose will be expressed as a unit vector. Okay, now I have to let you go, unfortunately. And we'll start with the exercises. So I'm asking you kindly not to do them for now, okay? It's gonna be hard. Because I need to show you first an example and then we'll do it. Just go through the presentation again and try to understand what we're trying to find, okay? And if you don't get it, please Google some stuff about directional derivative. Try to find it explained with different words, and I'm sure that you managed to understand the concept, the underlying concept. Okay, now I'm stopping.